Hey everybody, welcome back to another lesson in calculus. Can you believe it? Lesson 8, our last lesson of this first unit. Pretty exciting, huh? So today's lesson is about more limits at infinity. So when you're evaluating a limit at positive or negative infinity, you are allowed to use anything that you know from any previous math class or anything you figure out in this math class. So as I closed the last video, I talked about look for patterns. So, one of the patterns that we are exposed to early on, even in Algebra 2 class, is this idea that with rational functions, those are functions where the numerator and the denominator are polynomials, that you can find the horizontal asymptotes by remembering that if the degrees are the same, that the horizontal asymptote is the ratio of the leading coefficients. If the degree in the numerator is smaller than the degree in the denominator, then the horizontal asymptote is 0. And if the degree in the numerator is greater, then you know that there is no horizontal asymptote. So I've just kind of updated those rules for calculus because we know that a horizontal asymptote is simply a limit as x approaches either positive or negative infinity. So I recommend you still go through the algebraic processes we've been doing when you're not sure. But use this knowledge to check up on yourself, to check your work. And then sometimes, it can save you a lot of time to just jump to that conclusion. So let's take a look at our first example problem for today. And we will also see that sometimes you have to take limits inside of limits, and so any shortcut you can take can really help. All right, so this is a rational function because the numerator is a polynomial, meaning that there are no fractional exponents, there are no logarithms, trig functions, things like that. So we can use our regular rules. So let's go ahead and use our rules. The degree in the numerator is 5. The degree is the highest exponent on x. The degree in the denominator is also 5. So the leading coefficients, which are the coefficients on the highest degree term, is our horizontal asymptote. So our horizontal asymptote is 2/7, and that's going to be the horizontal asymptote towards the right and towards the left, because there's only going to be one of them with a rational function, one of them at most. So the fact that this limit as x approaches negative infinity is really inconsequential, because I know that that's the limit towards both positive and negative infinity. All right, let's take a look at another one. All right, now we got the limit as x approaches infinity of this. Now this is also a polynomial. It's just written in kind of a annoying way. So let's go ahead and simplify a little bit, kind of expand out that denominator and see if we can't make some sense out of this. 5x squared minus 1 over 3x cubed plus 6. Is that 6, right? 6x. All right, well, the degree on the numerator is 2, which is smaller than the degree on the denominator of 3. So this function has no horizontal asymptote. So the question is it going to positive infinity or negative infinity? We know, if we were to graph this function, what's going to happen, and I'm not exactly sure what these branches would look like. One's going to look like that, and one's going to look like that, but they're going to have this kind of slant here. So let's take a look and see what's happening. Well, we can plug in infinity. If I plug in infinity, I will get infinity squared times 5, which is infinity, right? Minus 1. But the key thing is that's a positive number. So it's a positive number on top when you plug in infinity. On bottom, this is also going to be a positive number. A positive number going to infinity. Well, a positive number divided by a positive number is a positive number. So we're going to say that this is a positive infinity. If you're not sure, go back to the algebra techniques from the previous lesson. All right, let's take a look at this one. We've got a degree of 3 on top, right? and a degree of 2 on bottom. So once again, I've got a degree of the numerator that is bigger than the degree of the denominator. Okay, this is also a rational function. We just need to simplify by distributing there on the bottom. So this becomes the limit as x approaches infinity of 5x squared minus 1 over 3x cubed plus 6x, making the degree on top 2 and the degree on bottom 3. Since the degree on bottom is bigger than the degree on top, we're going to say that this limit is 0 because this function must be having a horizontal asymptote at y equals 0. All right, let's take a look at our next one. All right, for this one, we've got a degree on top of 3, a degree on bottom of 2. So when the degree on top is bigger than the degree on bottom, that means that we are going towards an infinity. We just don't know which one. So let's figure out the sign. We can do that by simply plugging in infinity sometimes. Well, it's going to be indeterminate here. So I think we need to do our algebra. So I'm going to factor out an x cubed, and I get 3x to the negative 1 minus 5 over x squared times 2x to the negative 1 plus 3. All right, so that's going to reduce down to just an x on top, and we'll plug in infinity. I get infinity times 0 minus 5 over 0 plus 3. So the top is going to be infinity times a negative 5. So that's actually a negative infinity on top over 3. So that's a positive number. So that's also a negative infinity. So I used my algebra there to answer which one it was. You know, you might have been able to tell just by looking at it once you see some patterns. And that's certainly okay too. All right, let's take a look at the exponential function now. So these are not like example problems as much as they are just kind of almost definitions, but we need to get a few more things down before we go any further with this. So I've got an exponential function e to the x. Hopefully this graph is familiar to you. The limit as x approaches negative infinity, if we look at this graph, I think you would agree is definitely going to 0. Okay? So that's going to 0. And we can basically show that algebraically using the same way we did our polynomials. If I plug in a negative infinity, that ends up being 1 over e to an infinity. E to an infinity is a very big number, right? It's infinity. And 1 divided into an infinite number of things is going to 0. All right, now you can clearly see that this is going upwards forever. E to the infinity is infinity. In fact, we used that earlier. Any number greater than 1 raised to a power going to infinity is going to infinity. All right, well, now that we've got that under our belts, let's use it. Okay, so I've got this function right here. All right, well, what I'm going to do is I'm going to simply find the limit of this exponent and see if that limit is going to a real number or a positive infinity or negative infinity. So the limit as x approaches infinity of 8 plus 2x minus x cubed. Well, if I plug in infinity, I get 8 plus infinity minus infinity. Okay, so we need to factor out an x, and maybe you've seen patterns and you know what this is going to be, though. I'm going to factor out the highest power. It's giving me 8x to the negative 3 plus 2x to the negative 2 minus 1. When I plug in infinity now, I get infinity cubed, which is clearly infinity, times any x to any negative power. If x is going to infinity, that is going to be 0. So it's 0 plus 0 minus 1 is infinity times a negative 1. So this is negative infinity. So what we've shown is that this exponent is going to negative infinity. But what is e to the power of a number going to negative infinity? Well, we know that. We just saw it. It's 0. If we let, what we need to realize is that this is really the limit as some number n, if you will, which is the result, maybe I'll call it y, is the result of a plus 2x minus x cubed as I plug in infinity there. And this is y going to negative infinity. That's what's happening, is that we have a number here going to negative infinity, and e to a number going to negative infinity is going to 0. All right, so you have a practice problem to do. Please pause the video and give it a shot, and then unpause it when you're ready to go over it. All right, let's go over this problem. All right, the limit of the exponent. This limit here is going to 0 because the degree on bottom is bigger than the degree on top. So this value here is really e to a number going to 0. But what is e to the 0? That's 1. Anything to the 0 power is 1. So that value there is 1. All right, let's take a look at another function that we need to keep in mind. Okay, this is the natural logarithm function. The natural logarithm function is the inverse of the exponential. So you can see we flipped it over the line y equals x. And we're going to take the limit as x approaches infinity of the logarithm of x. You can see that it is increasing always, slowly, but it is definitely increasing. So this must be going up to positive infinity. What about the limit as x approaches 0? Well, since we only approach 0 from one side, we can really only talk about the limit from the right. The other one is undefined. But the limit as x approaches 0 from the right is clearly negative infinity, right? Okay, so let's use that fact to answer some questions. All right, I've got the limit of 4 plus 7x over x cubed plus 1. Well, because I'm going to infinity, the limit of the inside here, x cubed, is that's a degree of 3. This must be going to 0. And the limit as I approach 0 from a positive direction is negative infinity. But before I jump to that conclusion, I need to make sure that this expression is going to 0 from a positive direction. So how are we going to determine that? Well, if I plug in a number going to infinity, this would be a positive number on top. Agreed? And if we needed to, we could factor out highest exponent terms and things like that to get exactly the sign. But this one here is really not at all a mystery. We can see that the bottom is also positive. There's no minuses or negatives in there at all to have to worry about. And if there were, we would say it's going to take the sign of the biggest, the most dominant term. But this is a positive number. It's a positive number always, but it's a number going to 0. So that means it's a number going to 0 from the positive direction. So we can conclude that this is negative infinity. All right, you've got another practice problem to do. Pause the video, give it a shot, and then we'll go over it. All right, let's see how this went. Okay, so the numerator is x to the 4th. And the denominator is x squared. So this must be going to an infinity. Do you know which one? Is it going to... Oh, but it's x going to negative infinity. All right, well, let's figure that out. I'll tell you what, let's go ahead and find the limit here and see what's happening. Let's find the limit of the inside. I'm going to factor out x to the fourth, making this 1 minus 3x to the negative 3. And I'll factor out an x squared here. That gives me 1x to the negative 2 plus 2. Okay, so we are going to lose some x's, just as we thought. Ah, now I see it. Look at that. I only lost 2 powers of x, so I still got an x squared. So when I plug in this negative infinity, it's going to be negative infinity squared. That's a negative number going to infinity squared. When I square it, it's going to become positive. Well, that's going to be 0, right? Positive or negative infinity to a negative exponent. Boom, 0 every time. Don't even need to worry about it. All right, that's 0 plus 2. Okay, that's positive, that's positive, that's positive. This is a positive infinity. So the limit as x is going to positive infinity of the natural log of x. That's what you got to think about. What does the natural log of x go to as x goes to infinity? We saw that in the graph. It's a slow climb, but it is always climbing up to infinity. Okay, so one more function I want you to consider, and that is the arctangent. So here's the arctangent function. The arctangent function, by the way, is sometimes written tan inverse with that little -1 symbol. I usually like to use arctangent, but you need to know both because you'll see both. All right, the limit as x approaches negative infinity. Well, as x is approaching negative infinity, this graph is getting closer and closer and closer to negative pi over 2. And the reason why that arctangent would have a horizontal asymptote at negative pi over 2 is because tangent has a vertical asymptote at negative pi over 2. Likewise, as x is going to positive infinity, we're approaching positive pi over 2. And again, that's because regular tangent has a vertical asymptote at pi over 2. So if your original function f has a vertical asymptote somewhere, its inverse will have a horizontal asymptote there. Okay, so let's use that. We're going to evaluate the limit as x goes to infinity of inverse tangent of 2 minus 3x. All right, so when I plug in infinity, I don't think this is at all indeterminate what's happening on the inside. You know, if I was to evaluate the limit on the inside, I get 2 minus 3x squared. When I plug in infinity, I get 2 minus infinity, right? The infinity will go squared is infinity times -3 makes it minus infinity. 2 minus an infinitely big number is negative infinity. So this is clearly going to negative infinity. What does the inverse tangent approach as x approaches negative infinity? We know it approaches negative pi over 2. All right, one last practice problem, the last practice problem of the unit. Give it a try. All right, here we go. This is, oh, I pulled a fast one on you, didn't I? wonder if you got this one. All right, so arctangent. The limit here, the degree, this is a rational function, right? So if we take the limit of the inside, we know that that interior there is same degree, degree 1 over degree 1, so it's the ratio of the leading coefficients, which is 1 over -1, which is a -1. So really, this is simply the arctangent of a value approaching -1. Well, what is the arctangent of -1? In other words, where does tangent give -1? Well, that is at, well, that's, where is it? You need to know your range, don't you? What is the range of arctangent? The range of arctangent is the same as the range of sine. It's this range up here and down here. Okay? So we have to go from negative pi over 2 to positive pi over 2. We saw that when x goes to negative infinity, arctangent goes to negative pi over 2. When it goes to positive infinity, it goes to positive pi over 2. So these are all the values that are possible. So don't give me anything over here. That's not in the range of that graph that I gave you, right? Right? Should we look at that graph one more time, maybe? So this is the range of values that I can give. I can go from negative pi over 2 to positive pi over 2. So where in that range around the unit circle does tangent equal negative 1? Well, we know that tangent in the first quadrant, maybe you haven't memorized, that's 0 because it's sine over cosine. Sine of 0 is 0, cosine of 0 is 1. This one here at pi over 2, it's not even in the range, but that's undefined there. Right here in the middle at pi over 4, that's where the sine and cosine are the same. So they're both the square root of 2 over 2. So the tangent value there must be 1. So down here at negative pi over 4, that's where the tangent value is going to be a negative 1 because the cosine is still positive because x's are positive over here. So the cosine is square root of 2 over 2, but the sine is a negative square root of 2 over 2. So that makes that a negative 1. So we know that the answer here, when does tangent, for what angle measure is tangent negative 1? The answer is negative pi over 4. And that's exactly what that limit is. Isn't that wicked? All right. Hopefully you enjoyed that little prank. But no, those are good conversations to have. Kind of interesting, I think. So that's the end of this unit. I'm excited to see how y'all do on it. And then we'll pick it up with our next unit. Until I see you again, take care.